She's an expert about that, particularly the star 509 Cas. Okay, thank you very much.
Yes. I guess I met most of the people already, but those who don't know me, then I'm Anni. I'm a PhD student from University of Tartu and everything else that also Lydia said. So before we go to the science part, I have to give a short introduction of where I come from, just in case. So, I'm from Estonia, which is located in Europe, right here. And it's the northernmost of the 3 Baltic countries. So we got Latvia and Lithuania under us, and Finland up top. And the observatory is located right here in a small village called Taravera. And yeah, we got this nice white big building and quite a few telescopes there. The biggest one that we have is this 1.5-meter telescope that I have been using for my science as well, quite a lot. Most of my data is from that telescope. And we also have the 60-centimeter smaller telescope for photometric observations. I wasn't entirely truthful from where I come from, because I'm not from Tartu, I'm not from Taravera, I'm actually from northern Estonia, from a small town called Rakvere. And we've got this city symbol of a prehistoric ox and a nice 13th century castle in there. So if you ever get a chance to visit, it's a pretty nice place. Okay, and now we can go back to the actual subject at hand. So I was putting together this presentation and I was kind of thinking which are the main points I would like to make my presentation, what would be the most interesting cases to talk about. And I came up with kind of these 5 questions or topics which I would like to answer during this presentation. So pretty much first off, give an overview of the yellow hypergiants, the confusion about their evolutionary state, and then also how we can describe them. So their variability in luminosity or temperature, and how their mass loss can be described as well. And then, of course, the question of specifically V509 Cassiopeia. What has the star been up to in the history times, and what is happening to it now? And then another little add-on to it would be the connection to also more massive stars like B bracket E supergiants. There's a chat thing happening here. Okay. Just in case. Okay, so we have all seen this Hertzsprung-Russell diagram. I wish I had a laser pointer. Do I have a laser pointer? No, it isn't. Okay. No, that's fine. I'm just gonna wave my hands around. So here at the Hertzsprung-Russell diagram, the part that interests me is the part that's way up top. So, we got this main sequence here. Amazing. I just got a big stick to point at things. So we got the main sequence here, the giant branch over here. This is the boring stuff. What I'm interested in is the way up top where there's very few stars and where the most massive stars are located. I'm sorry if I said this is the boring stuff. It's not actually boring stuff. There's very interesting stuff happening there as well. But in this presentation, I'm going to talk about the up top. Yes? Excuse me? Okay. So, about the evolutionary state of massive stars. As I said, like the earlier mass stars have a pretty well-defined evolutionary track. When they run out of hydrogen, they leave the main sequence. They become this red giant stars. Helium ignites. They bridge up again and become this red giants until they run out of fuel and become planetary nebula and this little white dwarf. But with the massive stars, there's quite a bit more of so-called bouncing around happening. So as a massive star runs out of hydrogen, it also does a second sequence, but then it doesn't move up anywhere, it moves straight, I guess, to the right, and becomes a red giant, after which it becomes moving backwards again. But this kind of backwards motion, or motion to the right or motion to the left, isn't ooh. My stick got upgraded to a laser pointer. Amazing. So this kind of backwards or forwards motion that's happening here is not super clear when you're just observing a star, because you don't, from just one or two observations, you can't tell if a star is moving to the right or if it would be moving to the left, so-called, on the evolutionary track. And that can cause quite a bit of confusions when determining the evolutionary state of massive stars. Because, well, with the main sequence star, it's a bit clearer. So you can place the star on the Hespen-Russell diagram, and that kind of gives you an idea of the evolutionary state. It is a better idea. In the massive stars, that middle period between blue and red can be quite, you can get more questions than you have answers for. Okay, and we're still here up in the Hespen-Russell diagram, and here's a nice plot from Anna about a lot of different massive stars. So we got the bluer massive stars here on the left, red or cooler massive stars to the right, and then there's this middle part of populated by yellow hypergiants, or yellow supergiants. I'll come back to that. And then we can start drawing the evolutionary tracks, and the entire picture becomes a whole lot more messy, so to say. So the star goes to the right and then comes back to the left, but in some cases it might bounce back and forth multiple times, and if the star is supermassive, it will not even make it to the right. It will just stay here with the hotter stars. Okay, so I mentioned for a moment that whether it's a yellow hypergiant or a yellow supergiant, and how to classify a star as a yellow supergiant or a hypergiant is quite, I would say, it's not trivial. So there's been quite a few papers that classify the same star either as a hypergiant or a supergiant, and then they argue with each other, and there has, like, it takes time to reach a consensus about any single star. So hypergiants are massive stars with very high luminosity classes, and so are yellow supergiants. So you can't just say that hypergiant is more luminous than a supergiant. That's not necessarily true. But the difference between kind of yellow hypergiant and the yellow supergiant is that hypergiant is an evolved star. So it has already passed the red part of its evolution, and it's kind of warming up. It's moving back towards the blue that we were looking on the evolutionary tracks, while a yellow supergiant will be still evolutioning on its way from blue to the red. So still on the first parts of its evolution. And, well, how can we tell? We can tell by what we can see about the star's atmosphere. So yellow hypergiants generally have already lost a lot of their mass during their evolution and during the red supergiant stage. So they tend to have either a nebula around them or very large and extended envelopes. And in the star's photosphere, that would be very much motions or dynamical changes in there. Yellow hypergiants also pulsate. So the stars are always very variable and are subjected to multiple mass loss episodes. And this is kind of not the case for yellow supergiants. But to determine if a star is losing mass or if a star is having these extensive motions in its atmosphere, for that you need to have quite a lot of observations over an extended period of time before you can start saying something about the dynamics happening to the star. So the term of hypergiant, mostly the term is a description of the star spectrum as well. Okay, back to the Hertzsprung-Russell diagram. And so we are zooming in on the diagram again. So first up, we were looking at this big area, and now we are zooming into this region that has been interestingly named the yellow void. So, or the yellow evolutionary void. And here I have also marked the star that we have at interest, the V509 Cassiopeia, or one of its positions, current position on the diagram at least. And why? Our first question is why the yellow evolutionary void, of course. What creates this name? And this kind of void, part of its name came from the fact that in this region of the diagram, there are relatively less stars than in the previous or in the later parts, or more on the left or more on the right, so to say. So this is an area that is relatively devoid of stars, and it's kind of this instability area for massive star evolutions. So the void doesn't exist for yellow supergiants. They can evolve across the diagram as normal, but once the stars have evolved past red supergiant state and are coming back towards the bluer, then they encounter this region where their atmosphere becomes extremely unstable. And in this case, the star can be subjected to extreme mass loss episodes. So if you have to describe the void, then some people have modeled the properties of the star's atmosphere, and they found that the effective gravity can become near zero or even negative, which means that pretty much the star's outer layers become detached from its gravitational attraction. And due to all this instability happening in this void area, then it's possible that it is a very small blink in the evolution of a massive star. So the star could spend less than 10,000 years in this void region before either evolving forwards to the blue or going back to the red, or possibly going to the blue. We don't really know because we haven't really observed. So there's quite a bit of like conversation or ideas happening with what is going on with the star and what will be the future look like. Okay, so I pretty much already spoke what's happening here. So there's a negative density gradient. Okay, so there's atmosphere is extremely unstable, and pulsations that are happening in the star can cause huge mass loss episodes. So some pulsational motions can trigger an extensive or explosive mass loss, so to say. Okay, so yellow hypergiants. As I said, it's quite hard to determine if a star is a yellow hypergiant, so we only know 18-ish in our galaxy. The 18, I put a question mark in there because I think that number includes the stars that were counted as yellow hypergiants in Westerland 1, but there was recently a paper that they are not actually yellow hypergiants. So that number, don't quote me on this, it's very much up to question. And yeah, very hard to determine the evolutionary stage and located in the yellow evolutionary void. And here's a pretty picture. I love this picture. It's an artist's impression of V509 Cassiopeia. Okay, so going even more specific. Now we're not looking at the big part of the Hertzsprung-Russell diagram. We're not looking at generally the void. We are looking at one specific star inside the void. And that would be V509 Cassiopeia, which currently has a mass approximately 11 solar masses. But as it was a massive star, it's an evolved massive star, so it has lost about half of its initial mass during its previous evolutionary action. my God.
Before explosion.
That sounds like a mass loss. So there's a thunderstorm happening currently.
East sails.
Yeah. And V509 is, of course, a variable star. The variability lies in its luminosity or visual magnitude. The variability lies in its temperature. And the variability, of course, it's not a consistently variable star, so the behavior of the star keeps changing over time as we are observing it. And another very interesting thing about V509 is that it has forbidden nitrogen and forbidden ionized calcium emission lines in its spectrum. And this sort of forbidden lines are usually found in much, much hotter stars. So it needs a bit of explaining to do how these forbidden lines can be found in a cool star like V509. So if we go back to the earliest days of when the star was mentioned, then it seems like there's no record of this before the 1850s or so. It's possible that the star at that time was fainter than 6th magnitude and was just not included in the catalogs. But in the following 100 years or so, the stars brightened by another magnitude. And in the 70s, it was categorized as a variable star. So its magnitude in the first half of 1900s was about 6th or so, and at the end of 1900s it was near 5/5 magnitude. Okay, and here's also some plot of the historic data. So we can see quite a big variability behavior in the stars, so about 0.2, 0.3 magnitude, amplitude. And it seems like over time, the stars seems to have been going slightly dimmer in the late 1900s. And here we have some data from our very, very active observers at AUSO, which can be freely downloaded from the AUSO website, and that we use in this research as well. And we can see that the variability, or the magnitude of the star, has pretty much evened out at 5.3-ish. So there's not, in the last 8 years, there's been no kind of this trend of the magnitude decreasing anymore. And also the amplitude of variability has changed, has decreased. So it's now like 0.1 magnitude or so. Okay, but this data looks quite, so to say, messy. Also, the errors are a bit big. And if you want to give a better overview of the light curve, we have to smooth it a little. So that's what we did. We applied a smoothing window of 30 days. And this kind of gives us a much better overview of the variability of the star. And of course, to check if our smoothing is a proper thing to do, or we're just doing it, without reason, then we have observations from test satellite. And the test satellite errors are smaller than the data point size. So if we plot the test measurements over our smoothed light curve, we can see that it matches up really well. So we have very strong reason to believe that the star's luminosity is not jumping up and down, but the changes are smooth. Okay, and then we add some more data from the blue is still the AUSO light curve. Observer was Bormann, and the orange is from AUSO's Bright Star measurement program, which has been done by a couple of telescopes. as well, so additional V filter data from there. And we also added Gaia data to increase the length of our timeline. And after we got this longer timeline of data, we can, of course, look at the periodicity in the light curve. And we kind of confirmed that the periods of these fluctuations are somewhere between 100, 200 days or so. The periods is not consistent, so it's kind of quasi-periodic variability, and the periods keep changing over time. So kind of the period lengthens or shortens, and it's no certain value that can be given. But if you kind of keep looking at this light curve, it seems that if we take out these shorter periods, then we found that there is slightly another longer period that starts from here, goes up and down and up again. So there seems to be this kind of long wave of 1,000 days or so going through the data as well. And if we went back to the old data and tried to see if this longer wave is apparent there as well, then we found that no, it isn't, because once we remove the trend, there's only this short-term fluctuation without any long-term variability. So yeah, seems like that is a new thing the star is doing. Okay, so V filter, check. Let's check the color of the star. So here is a B minus V color index light curve from also 1975 to the end of 90s. And the color over time has been getting bluer and also showing similar kind of variability motion as we saw in the V filter light curve. And when we take our current measurements, not a big surprise that the color also in the last 8 years has pretty much evened out. We don't see this trend of the star getting bluer anymore. And also data and bright star monitoring data here on the same plot. So we can see that also has quite a bit larger error bars, but the bright star monitoring seems to show that also data is still quite well in describing the variability in the B minus V. Okay, so when you put everything together, so this blue-green cloud of data here is the same as this data on this plot. And this orange bunch of data up there is the same as the orange bunch of data in here. And when we put them on the B minus V to the B magnitude plot, so the B magnitude data is from the plot that I showed earlier, then we can see that there has been this consistent trend over time of the star's color. So the dark blue here down in the right is the oldest measurements, and the greener it goes, the newer the measurements are. And topping off with the orange measurements from the current work. And a couple of things that you can see is that this kind of variability seems to have stopped, or the trend that we can see in the older measurements seems to have stopped down or leveled off up there, and that the amplitudes of variability have decreased quite a bit. So when we compare to the data from the 90s, we can see a lot of amplitudes, or quite large amplitudes in the variability, and if we look at the current data, the amplitude is much, much smaller, about 2 or 3 times. So the star's atmosphere overall seems to be stabilized. Okay, another thing to look at is we can look at the temperature. So here is data from Tartu Observatory and also the Nordic Optical Telescope, and the whole temperature curve covering the last 8 years. And here we can see that it's average around 7,800 Kelvin, and with a few dips here and there, but it's pretty boring graphs. I have everything seems to have evened out or reached a certain level. But it's much more interesting when we put it in the historic context. So here we can see the temperature variability from 1950s to the current data we have. And the old data gives us quite a good overview of about the mass loss motions of the star. So as the star loses mass, then the ejected matter forms this cooler pseudo-photosphere around the star. And as this cooler layer dissipates over time, then we observe that the star's temperature is increasing again until the star loses mass again, and the ejected matter forms this cooler layer around the star. And this kind of motion can happen many times. And in the history of V509, it has happened at least a couple of times. So the first dip that we see in around 1973 lasted a few years until the temperature recovered. When the temperature reached a higher level, then at the end of the 1970s, it dipped again before it started recovering. So at least 2 occasions that we have seen, in which case the temperature drops about 1,000 degrees and then reaches the previous values or even higher than previous values, at which point the temperature drops 1,000 degrees again. And for that same reason, when you read the papers written in the 1990s, then people had temperatures near 6,000 degrees. And they had already seen that with the motions of the star, then the star will probably lose mass and it will become cooler again. And this did not happen. There was no mass loss. The star became hotter and it became hotter and it became hotter until it reached about 8,000 degrees, at which point it seemed to have leveled out a bit. So that happened in the beginning of 2000s. And we can see this cloud of data here in the beginning of the 2000s and our cloud of data in the blue also. So the star's temperature seems to have pretty much leveled out over there. And when we observe, or when we looked at the data, then it's also apparent then that the temperature variability in the early 2000s compared to now is much smaller. So the amplitudes in the temperature have decreased as well. Another sign of the star having reached a more stable state. Okay, another interesting thing, of course, to look at the spectrum is the radial velocity of the star. In this case, I have separated Tartu Observatory and Nordic Optical Telescope values, just to illustrate that, well, in Nordic Optical Telescope, we have used the shell spectrograph VS, which achieves radial velocities with accuracy of a few tens of meters per second. And Tartu Observatory, our spectrograph is in Cassegrain, so the radial velocity errors are a bit bigger than for PS, but we can clearly see that the measurements agree really quite well. So, and yeah, we can see that the radial velocity variability is up to 20 kilometers per second or so. And this variability seems to be pretty consistent over the last 8 years. So when we looked back at previous research done on this, then it seems like the radial velocity has always been like this. So we go back 10 years, we go back 20 years, we see similar values of radial velocity. We go back 100 years to 1920s, where V509 was described in a paper, and the radial velocity variability is the same. So that was quite an interesting find, because over this time, since 1920s, the star's temperature has increased from 5,000 degrees to 8,000 degrees. And we saw similar changes in B minus V and the V magnitude. But overall this time, radial velocity hasn't done anything. The amplitude is very similar, and the level of radial velocity, so the systemic velocity of the star, is near -60 or so. So yeah. Oh, and the lines that we used to measure radial velocity were these ionized silicon lines. Here's a couple of examples. So one at high radial velocities and the other one at low radial velocities. So they're pretty good, strong lines that we can use a Gaussian approximation for the measurements. Okay. And now we go more away from the atmosphere of the star and kind of looking at the surroundings of the star. And for V509 Cassiopeia, there has been no indication of a nebula or some large-scale structure around the star. But we are seeing these emission components in the spectrum, and we are seeing these forbidden lines that I mentioned earlier. So the structure that causes these lines should be somewhere closer to the star, that we cannot detect it as a nebula. And a possible explanation to this would be some disk-like structure. So for this example, we have a scandium line on two different dates. On one case, it seems like the red wing of the line, or like the wings, emission wings of the line, are about the same strength. And in another case, it seems like the red wing of the line is much lower than the blue wing of the line. So the line is variable, and the line is variable seems in emission lines components vary, and also the radial velocity of the line varies. So let's take the line apart and see how it is formed. So the central absorption component varies together with the radial velocity of the star, the plot I showed earlier. So the central component of the line would be formed in the atmosphere, or in the photosphere of the star. So as the star pulsates, the central component will either move more towards us or move away from us with radial pulsations. And then the emission wings, in the case that they would be formed here in the disk, the emission wings would actually not be affected by the pulsational motions. So that if we think that the emission would actually be the same, not variable. So if we have the same strength of emission all the time, and we vary the position of the absorption component, then we can see that as the absorption component changes its velocity, it will kind of eat the wing it is closer to. So in this case, on the red line, this absorption component would cause the right wing, or the redder wing, to be smaller than the bluer wing. In the case of the blue line, so the absorption component is more in the middle, then we can see that the red and blue wing are about the same height. Okay, but what's the cause to believe that the emission isn't changing? Well, we are seeing the forbidden calcium line. And the forbidden calcium line on similar dates is not variable at all. In fact, on all the dates that we have, the forbidden calcium is the same. The line constantly looks the same. And forbidden calcium is kind of one of these lines that has been used as an indicator of a disk-like structure in the case of B bracket E stars. So, as we know that in one case of a star, this line is formed in the disk, then we are seeing very similar line in the case of V509 Cassiopeia with a very similar shape. And we are also seeing that the disk structure would explain the emission components in other lines that we are seeing. So this is kind of our reasoning to think that there would be a disk component of the star. But let's look at all the data at once. So we have a lot of calcium lines. Calcium, no, that's scandium. A lot of scandium lines over a lot of dates that we can plot over each other, and we can see that the components vary quite a bit between the dates. Okay, and let's now squish all of these observations together and make this sort of height map. So in this case, the central absorption forms this blue part here in the middle, and the two emission peaks form this kind of red mountains here, minus 100 kilometers per second, and here near 0 kilometers per second. There are two red mountain ranges, and with a lake or absorption in the middle. And as we put all of the observations we have on a big long height map, we can also plot over it the silicon that we use to determine the radial velocity. So we can plot the silicon over it with the radial velocity of the star. That is this black dotted line in the middle. And well, as we can look at the map, we can sort of see that as this black dotted line bounces left and right, the blue absorption in the middle behaves very similarly with the bounces. And we can also kind of get an overview of whether the red wing or the blue wing is stronger at any point of time. So as the absorption component is more towards the red, then we can see that the blue wing is stronger. As the absorption component is more towards the blue, then we can see that the red wing would be stronger. So that is kind of an overview of all the measurements that we have over 8 years. Okay, and then we can put the correlation plot between the radial velocity and the ratio of the scandium wings. And there's a bit of a spread in the plot, but there seems to be a quite consistent, at least, correlation between the two. And these points that I plotted orange show the same measurements I had in the previous. Okay, so I have talked about 40 minutes now. And I think I hope I gave a bit of an overview of what's been happening to V509 Cassiopeia, both in the past and well, the star has pretty much stabilized in the last 10 years or so. And we see stabilizing in the temperature, the V magnitude, the B minus V, and also a few other things that you can hopefully read about in the paper soon, since I submitted the paper 3 days ago. So fingers crossed. And yeah, seems to be a bit of interesting like correlation or similarity between B bracket D stars and the yellow hypergiants. And who knows, maybe a yellow hypergiant could become a B bracket D star in its future. Muchas gracias. Yes.
Maybe. Thank you. That's very nice and exciting results. There are two things. In the beginning, you mentioned I like that you have so many pieces of this puzzle, and you are putting them together. And you mentioned in the beginning that this object is a binary or not. There was something.
Yeah, it's a binary star.
How does this binarity fit into this?
So that's a very interesting question, and there have been quite a few researches over the years about trying to determine the period of the binary, and the results range from 600 days to 600 years. But the current consensus is that it is a very wide binary. So the V509 Cassiopeia would be evolving as if it is a single star. And the way that we kind of see the binarity is the interaction in the wider environment of both of these stars. And that in this environment, we see the forbidden nitrogen lines. And these lines need very high temperatures to form. So it is kind of hypothesized that the binary, the companion is a B-type star, which is quite a bit hotter than V509, so that the companion would excite this overall environment around both stars and create these forbidden nitrogen lines. But yeah, technically they should be evolving as single stars. That's the assumption, at least.
And then when I saw the plot of color versus V minus V versus V, I was like, it was not the usual structure of V versus V minus V, so
it was not?
Well, yes, it was.
I don't
It
know.
was a perfect diagram. It was a perfect. So, like in my mind of having the color magnitude diagram, yes, I have to spend sometimes thinking of how to use the. Sorry, it's like. It took some time trying to see how it looked in the color magnitude diagram. So the idea is that it was.
Yes, I can.
But it's similar to I was expecting to see this.
Okay, that's fair actually.
Because
yeah, that's a good point. I never thought of this diagram as a color magnitude diagram actually. I was mostly looking at how these things are working together. What's the correlation? So I'm mostly looking at this as a correlation plot that evolves in time rather than a color magnitude diagram.
I was seeing the evolution of the color magnitude diagram and trying to see how it got into the yellow. Like coming from there. No, the other way. It was this getting hot.
Yeah.
That one describes quite well actually the magnitude versus temperature.
Yes. But so it is becoming less bright, and it's becoming
yes, and it stopped getting blue, yeah, or it was getting bluer, and now it's kind of leveled out at this point, yeah.
Yes, it's very nice.
Have you attempted to measure the change of the radius of the star due to the change of the temperature?
Radius, no, I have not attempted. Sounds complicated. Okay.
Because the distance is the same.
No, but determining the distance of the star was actually something that we tried to work on. And well, Gaia isn't good for such bright stars, and then we need to find some different ways. And we tried to see like the stars in the same OB association. Maybe we can determine the distance from those and then kind of interpolate or something. But it ended up as not being results we could publish in a paper.
You show some variations in the temperature. How do you measure, or how do the authors measure the temperature?
I am so glad you asked. I've got extra slides. Okay. So bear with me. Okay. So in theory, let's start actually from the next slide. People have used different ways to determine temperature, but in spectroscopically, it is often the case of taking an ionized line, taking a neutral line, finding the ratio and relating that to the temperature. So what people have used for this kind of massive stars is the iron 1, iron 2 line ratio. And in this one plot, we have this iron 1, iron 2 ratio versus the effective temperature of the star. And the effective temperature of the star in this case has been found through modeling of the stellar spectrum, so through Kuros models or something else. And on this plot, we have plotted some other supergiant stars, and we have also plotted V509 Cassiopeia here as well. So in this case, we can relate the iron line ratio to the temperature of the star. But the spectra in Tartu Observatory do not include these iron lines, and they don't include any other iron lines that we could use to determine the temperature, because iron lines tend to have these emission wings also, and which means that the line is kind of ruined as we cannot accurately measure its depth because there's an emission in it. So we need to find some other lines, and two lines that are in the Tartu Observatory spectra are this calcium 1 and iron 2 line, which are very nearby, but they're relatively weak. So, but they can be used. They don't have the emission wings, and they are the separate lines that you can clearly see in the spectrum. So we have related the effective temperature that we got from the previous plot to the ratio of these calcium 1 and iron 2 lines. And then we get this sort of curve here that we can use to get our effective temperatures. So there's a fit to this curve. Of course, there is quite a bit of uncertainty in this determination way. But if we look at these calcium and iron lines, then one of them is stronger at higher temperatures, and the other is slightly stronger at lower temperatures. So here, when the temperature is 7,800, which we see with blue, then the calcium line is quite weak, while when the temperature is lower, 7,500 or so, then the calcium line is much stronger. In the iron line, we see a bit of a less of the change, but there is still change in the intensity of the line. So we find these line intensities, we use the pretty plot we got here, and we get the temperature.
Perhaps you already told us this. I want to tell you to ask you about H-alpha line profile. How do you see? Is there variability in the line?
There is variability. There's a lot of variability in H-alpha. The H-alpha, it's in absorption, it's in emission, it's in absorption. There's at least 3 components in the H-alpha line coming from different distances from the star and kind of forming this composite profile. That there was actually a paper 4 or 5 years ago that went further in depth of the variability of H-alpha line. But there's quite a bit of variability there as well.
So the same the analytic cost for this magnetic diagram.
Okay.
Have you actually looked more closely at the data? What actually happens inside those blobs or in the right part was this kind of.
You mean the blob?
Why? What actually happens there? How
The blobs? It's the same as here. This is what happens.
Okay.
This same data is here on this diagram in B minus V, and this data here is the data that's here in B. So
it's kind of running circles in orange.
So in the orange, it's this data here that is orange, P minus V, that we see the variability. And the orange V data is the orange here, V data.
But what is happening inside the blob? Is there kind of just randomness, or is it some specific pattern? Because for example, V stars, they usually show very specific patterns.
Okay, so you mean if there are formed some circular motions here, or
Maybe, I have no idea.
I tried the first version of this plot, I connected the dots, and it was just a complete wave of a mess that wasn't at least from these measurements, it wasn't apparent what was happening, but these measurements also, well, there's quite a long gaps in the earlier days and so on. I have not looked inside this flow to be sure, but it seems like with the variability we're seeing, it's just left and right and left and right and left and right.
Do these stars have dust around after expanding the material?
There is no infrared excess.
So there is no dust.
There is no nebulosity or no this infrared dust to be, well, at least nothing that forms this kind of layer.
What is the criteria to search yellow hypergiants? Because we have 10.
Luck.
What is the difference between yellow hypergiant and they look the same?
So yeah, there is this kind of timelines of data of showing a lot of variability in the spectrum of the star. Then people say that, okay, there's so much, then we can see emission lines and there's so much variability, there must be large scale motions, it must be a novel star, so it could be a yellow hypergiant. And in some cases, people say, oh, it definitely is variable. It could certainly be a yellow hypergiant, which was the case of Westerland 1, which is this cluster that has a lot of evolved massive stars in it. And then recently there was a paper at, guys, these are not yellow hypergiants, they're just yellow supergiants. You were wrong, pretty much.
I can add to that we had a big trouble of publishing raw Cassiopeia, not even by the raw Cassiopeia paper. Because the referee did not agree this is hypergiant. It is supergiant, full stop. I do not agree with you. So there was a lot of fighting. We did not go to the consensus. It was finally solved by an editor who said that, okay, you may have a disagreement, but you can still publish a paper. But it took a long time. And finally, referee did not agree that it is a hypergiant. That it is supergiant. It's going from base sequence to the full stop.
Sometimes it's supergiant, sometimes it's supergiant.
Anyway, so there is just to support the figure. There is no consensus.
So now it's more or less naked, the sense that it has everything.
Yeah, pretty much. So you can see the star, you're not seeing this nebulosity or anything there.
Yeah,
if there's a mass loss now, I'm surely writing a PhD thesis about it.
And are you studying another yellow hypergiant?
So I'm actually pivoting off to another very interesting star that was doing interesting stuff, not like V509 Cassiopeia, which has been pretty stable lately, but actually the RWSFA, there recently was news that it has been up to something. So we'll see. We'll see what we get from there.
See if it is similar.
Maybe it's a hypergiant.
Maybe.
Maybe. Spoilers.
Being, hypergiant.
You're spoiling it. Let me write the paper first. Come on.
There is also consistent monitoring of hypergiants in carbon. These are all Cassiopeia, and then as they see three of them. So they have a lot of spectra.
So there are very few, but all of them in Cassiopeia.
There's a lot in Cassiopeia actually, and there's quite a lot of yellow hypergiants in the northern sky and very few in the southern sky. So I think the southern sky is still unexplored for yellow hypergiants.
And would you have any, I don't know, campaign or like opinions to look for these hypergiants following, I don't know, in a certain wavelength range or having certain variability?
I think that now that we have so many surveys that are either starting or just started, then we're going to have these huge piles of data from like JPAS, Formos, or I don't know, tens of other surveys that are charting both southern and northern sky. And I guess once we're starting to go slowly through this data about the stars, possibly not with like human eyes, but we need AI for this pile of data, then we might start finding more and more of these yellow hypergiants, hopefully. And I have more work to do.
The thing that you have here only one object, and I don't know, 20 years ago it was one thing, and now it's another one, and it's the same object. That's tricky and very.
So this is stellar evolution in human time scale.
And that's why I would like to see this plot in the bigger, the first HR diagram that you showed, to see the real evolution of this object. That would be nice to see.
There's a bit of a hint to this from the Anna's plots.
Yeah.
That there is this nice plot of this yellow void, and then they mark the positions of some yellow hypergiants. So there's these 2 points and a dotted line between them that shows the variability range that has been detected for these stars.
So that would be like in 8,000 versus
8,000 to like 4,000 or 5,000 ish.
Yes.
Here, yeah.
But this is outside the evolutionary track.
Yeah. I mean, you can just draw another track just below it. Because we're missing like 7 solar masses in the between, so it could be in the.
It would fit if the luminosity is lower, right? Because the track that 25 solar masses have the range of variability of the stars, considering
What about
the amplitude of the track.
the temperature variation is, it has some, the variation is in human landscape, it can be some years that it goes from the minimum to the maximum.
So this is
So maybe the evolutionary track doesn't touch the.
maybe.
There are two theories, I would say. Some people say that everything which we see with the temperature, it is only pseudophotospheric. Then nothing happens with the star itself. We only see the ember. Then there are other people who say that okay, this pseudophotosphere star, it is only for this bursts. When you see like this 1,000 degree up, down and then up, this is good. But this heating up, it is a real stellar revolution because if you take the time scale within that part of evolution, it is very, very fast. So that is the reason why it's void, because it starts to go through this very fast. And this heating up, you see the real stellar revolution. And this is actually Alex Lopez's point for this stuff. So, but there are kind of conflicting descriptions, or not conflicting, different models.
So we don't know whether it's revolving, we don't know whether it's a hypergiant or a supergiant.
Models.
Yeah, well, the model similar.
Continues.
It's not even on the model.
No, these are.
Then it bounces back, yeah, then it goes again, but then I mean, you can change the bouncing against yellow void. I think
Bouncing against yellow void, yeah.
Bouncing against.
So the star's temperature, it starts from cooler, then the temperature increases, it reaches the yellow void, it loses mass, it bounces back from the yellow void, it heats up again, reaches the yellow void, loses mass, bounces away from the yellow void, heats up again, you get the idea.
Now it is always.
And now it seems to be inside the yellow void, which is interesting for this because a very nearby star, Rho Cassiopeia, in the 1970s or so, these were spectroscopic twins. You couldn't tell the difference whether it was V509 you were looking at or Rho Cassiopeia you were looking at. They're practically the same looking star. And then recently, we probably know about Rho Cassiopeia, it has had multiple outbursts, smaller and larger ones. And then V509 Cassiopeia was like, yeah, I'm not doing that. So it heated up and is in the void right now.
But so both of them from the 70s, they were both.
In the 70s,
Both, and now they are both.
no, in the 70s, they were both like cooler, heated up, bounce against the void, cooled down again. Rho Cassiopeia still continues this bouncing.
Okay.
So it's hotter, it loses mass, it cools down, it heats up again, loses mass, cools down, but V509 stopped bouncing and now reached like this 8,000 degrees, which is much hotter than it has ever been.
Yeah, I asked about the temperature determination because in the summer school, my project was about Rho Cassiopeia and the variation of the temperature, what is the name? The force, the strength of the H alpha line and all the correlations we could find in those parameters. And I use I think it's the same idea of the ratios between the
Line depths, yeah.
The ion lines.
And if you had long spectrum, you will have the iron lines available for you. But for us, we needed to do some extra calibration because we have long slit spectra with a few hundred angstroms only, so we can't observe those ion lines in that spectrum.
I mean, you know, how well it is volumetric, absolute volumetric.
How the hell you are?
No idea. No idea. Somewhere up there.
So that would be support, maybe this, that also was asked here, that maybe which would be on the bit lower in this diagram.
That is possible.
The one where you showed the yellow wave.
So we tried to find the distance, and the goal was to use this distance to get the absolute magnitude while using interstellar Redding maps and so on. And the distance finding methods didn't really get us anywhere closer to finding the value. So I think at this point it would have been so much work to try to get any kind of more or less measurement that we just kind of needed to put the paper together.
So it's not part of any cluster or association.
It's a part of association. So there is distance determinations in previous papers, but we can't get anything better than what there's already there.
Technical thing in terms of global business associations.
We had tried actually to do that, but I think just this year we observed that there is some heteros, whatever association, because the star is very close to the Professor Leah and the forward. And unfortunately, for the law, there is no data in this part of the sky, so we wanted to measure those stars and figure out which ones have the same those velocities, and then also the kind of normal supergiant stars.
I'm not sure you have mentioned also this diffuse interstellar band. Because if the same diffuse interstellar band in several spectra of nearby stars, so they are like really physically also nearby, not just on the same line of sight.
Near to each other.
Near to each other, yes. So they are like really in space near to each other.
That's what we try to do.
Yeah.
Maybe we'll do some more observations.
Yeah. Unfortunately, this star, which is extremely interesting, but unfortunately being too bright. A bit too bright for higher,
Yes.
as usual.
Okay, anything on Zoom? No, I
They
can't.
left.
They left.
After 3 hours.
It's been 3 hours. Okay. I also showed my extra slides, so I don't have anything more to talk about.
You have extra?
I had extra slides, but I got the questions, so I was happy.
Oh, you can show us. You can show.
Show us this.
No, I showed you the extra slides.
Okay, good.
These were the extra slides. those credits.
Yes.
Credits.
Okay.
Credits.
But it's interesting that the radial velocity is -50. So it is in the equator, in the galactic plane, or is higher in the galactic plane?
It's in Cassiopeia.
I think it should be.
Yeah.
Close to the galactic plane.
Yeah, it's in the galactic plane.
Can derive the distance using the radial velocity because it's -50 or -60.
You have temperatures there.
Ah,
The radial velocity shifted -60 and it keeps constant.
yeah, it's
Almost all the period was around -60.
yeah. I mean, the -60 has been always.
Also the forbidden lines show this radial velocity. So if it is in the galactic plane, you can use the rotation curve of the galaxy to estimate the distance.
Yeah.
As a way to, it could, of course, couldn't fit, but if we assume that really it is following the galactic rotation, so you can make a rough estimate of the distance of the stars, considering that
That's interesting, yeah.
kilometers per second.
Yeah,
Yeah.
yeah. That's cool.
And then you can learn the rate.
Yes.
Because the meter sometimes is quite good, except when you have a double value, that then you have to choose if it is the closer or the larger value, because that depends on if it is outer or near to our orbits. That depend on the galactic longitude, but it's a way to estimate.
Yeah.
Are there any estimation of this same as science thing? The rotation?
Rotation. The lines are wide,
Yeah.
and that's all I can say.
Yeah.
The lines are about
So-
like 50 kilometers or more wider than that. I can't say the rotational velocity, and actually I don't remember from the top of my head any paper that had the rotational velocity. Probably it's out there, but from the top of my head I can't say, and I didn't calculate it.
Is it so that if you have such a star and you have rather lines, maybe it reflects the rather spherical,
Yeah, that's it.
not the rotation itself,
Mhm.
or all this, I don't know.
Yeah, that's for sure.
Movements.
This that you mentioned, very interesting, is the peak separation, I don't know that.
It's almost 100, no, 50,
Yeah.
yes.
70. 70 is about the separation between the peaks.
Should I have also a question about this one? You actually mentioned that this forbidden lines, they are most probably excited by the companion.
Forbidden nitrogen. Only forbidden nitrogen, not the case for calcium.
Okay,
Forbidden nitrogen needs this very high temperature. For forbidden calcium, this V509 itself is enough.
You mentioned that H alpha have lots of structures, and I suppose wind and different stuff.
Mhm.
Is there any contribution from this piece, or it's completely different?
Probably there could be, yeah. Because there's part of the contribution is like this H alpha from very far away from the star. Part of it is the star itself, but there's quite a few different components to it, and part of it could of course be from the disk. But in the context of disk, I have not looked at H alpha because it has so many other variables happening to it that to clearly distinguish which part would be from the disk and which not is like really, really difficult.
Has this been observed?
V509?
Right?
I'm sure there was some carbon oxide measurements of V509 done in near infrared. There was a paper about that. They were looking at
CO,
CO, yes. So there are some measurements out there.
yeah, so if this CO also have rotational structure, then you could assume the Keplerian disk, and then assume the Keplerian disk. Then from the peak separation, you can calculate how far from the star the calcium line appeared, how far this CO line appeared. The next slide.
For the reader. Yeah. Right. So we need photo evidence for